Hello, and welcome to one of our last lessons in Chapter 8. So, today is a big lesson. Limiting and excess reagent problems is one of the sort of hardest topics in Chem 20, and it's just because the questions take a lot of time to work through. You're going to discover today that when we do our 2 example questions, they take like 5 to 7 minutes each to work through. So, there's quite a few steps, a little bit of math. It just takes a bit of time to kind of get your head around them, but don't panic. Don't worry. You'll get it. It just takes a little bit of time, and we'll go through it and step by step and carefully. So we're going to start off with sort of a more common type example just to get you used to the idea of what does this all mean, limiting an excess reagent. So the scenario that we have is the following. You look in the fridge and you see that you have 20 eggs. That's a well-stocked fridge. And you have 3 cups of sugar, probably not in the fridge, probably in the baking cupboard. So 3 cups of sugar, 20 eggs. And you're going to make some cookies. So the recipe is below to make a dozen cookies. So here's our recipe. So the idea is that we're kind of comparing this recipe to a balanced chemical equation. So it's sort of like 4 moles of eggs plus 6 moles of sugar makes 12 moles of cookie. That's the idea behind this analogy. Okay, so which ingredient will we run out of first? We have 20 eggs and 3 cups of sugar. Which ingredient will we run out of first when we're trying to make our cookies? Which one is limited or the limiting reagent? So you can probably use common sense to recognize this one, that it is going to be the 3 cups of sugar will be used up before we ever run out of eggs. So this is called the limiting reagent. So the eggs are the limiting reagent. They are going to determine how many cookies we can make, not the sugar. We say that the sugar is in excess. I wasn't paying attention. I was erasing. The eggs are in excess. The sugar is the limiting reagent. Okay, what is the egg to sugar ratio? So this is like a molar ratio from a chemical equation. And so it is 12 cookies gives us or uses up 4 eggs, or 12 cookies uses up 6 cups of sugar. So those are our molar ratios for this balanced equation. So we're going to try and figure out how many cookies we could actually make if we have 3 cups of sugar and 20 eggs. So this is the pattern to solving limiting reagent problems. You solve them twice. So we're going to start with 20 eggs, and we're going to see how many cookies we can make using our molar ratio. So what we're looking for on top, we can make 12 cookies for every 4 eggs. Okay, so 20 times 12 divided by 4 is 60 cookies. Okay, hopefully that makes sense to you. If we have 20 eggs, that's enough to make 60 cookies because 4 eggs makes a dozen. So 20 makes 5 dozen or 60 cookies. Okay, well, let's see what the sugar does for us. So we have 3 cups of sugar. Okay, how many cookies can we make? Well, we can make 12 cookies if we have 6 cups of sugar. So you can see it's a molar ratio. We can cancel out the cups of sugar, just like we could have canceled out the eggs there. 3 cups times 12 cookies divided by 6 is only 6 cookies. So we only have enough sugar to make 6 cookies. So this proves mathematically that the sugar is our limiting reagent and the eggs are in excess. Okay, so that's the theory behind these. Do you think you have it? Excellent. Oh, I know, bad joke. Cracks me up every time. It's one of the best yolks I got. Oh, terrible. Dad puns. Oh, okay. So now we're going to look at some chemical reactions. Okay, so in this diagram, so this is showing it to you as a model. We have 10 hydrogens. That's these little guys. 1, 2, 3, 4. So 10 moles, 5, 6, 7, 8, 9, 10 moles of hydrogen. And we have 7 moles of oxygen in red. When they react together, we end up with, let's see how many water molecules. I'll switch my colors here. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we finish with 10 water molecules, and we have 2 oxygens left over. Okay, from looking at that, you can tell that the oxygen is in excess. It's left over, or some of it remains. If oxygen is in excess, that means hydrogen must be the limiting reagent. It's all used up. Okay, so let's take a look at this. The definition of a limiting reagent is the reactant that gets completely used up in the reaction, while the excess reagent has some mass remaining after the reaction is complete. So we have some oxygen remaining after this reaction is complete. If you wanted to prove this one with math, here's how you would do it. Here's the pattern. So it's just like our cookie recipe. We have 10 hydrogen. How many waters can we make? Well, 2 waters are made for every 2 hydrogen. So it's stoichiometry. Hydrogens cancel out, and we get 10 waters. And that's what we did get, 10 waters, okay? Well, what if we use oxygen? So there are 7 oxygen, and from our balanced equation, we can make 2 waters for every 1 oxygen, which is 14 waters. So we can make 14, but we don't have enough hydrogen. 10 hydrogen limits us to 10 water. We'll never get to 14 because the hydrogen is the limiting reagent. So the trick is, whichever reactant makes the lower amount of product equals the limiting reagent. So that's the trick. Reactant that makes the lower amount of product is your limiting reagent. And the one that makes the larger amount is in excess. So this is what we did with the cookie recipe. This is what we're doing with the water recipe. So this is the big idea for today. And the rest of today's lesson is just actual problems with real numbers and math. Okay, so let's take a look at a couple problems here. We'll do 2 of these. These are from your textbook, and I'll do just the first 2. Okay, so for each of the following combinations of reagents, identify the limiting and excess reagents and find the chemical amount of excess reagent that will remain unreacted. Tricky. Okay, so for every one of these, you need your recipe, you need your balanced chemical equation. So we're reacting methane with oxygen. So methane reacts with oxygen. I'm going to skip states just to keep this moving along. So carbon dioxide and water, anytime you burn, this is combustion, burn methane with oxygen, that's a hydrocarbon combustion. Okay, balanced, 1 carbon, 4 hydrogen, 1 carbon, 4 hydrogen, and our oxygens end up being 4 oxygens on both sides. Okay, so there's our balanced equation. And it's telling us we have 10 mole of methane, 10 mole of oxygen. Okay, which one's the limiting reagent? So to solve these, pick a product. Doesn't matter which one. So I should say pick any, believe it or not, that says any product, and solve. So let's pick one. We'll go with CO2. So I'm going to solve this twice to see how much CO2 we can make. So 10 moles of methane times 1 CO2 for every 1 methane. means we can make 10 moles of CO2. Methanes cancel out. Okay, we're going to try it again with the oxygen. 10 moles of oxygen times 1 CO2 for every 2 oxygen equals 5 moles of CO2. So using methane, we can make 10 moles. Using oxygen, we can only make 5. So our rule, whichever reactant produces the least amount of product is your limiting reagent. So O2 is the limiting reagent. Another way to think of it is once all of the oxygen is used up, we've made 5 moles of CO2, the reaction is done. We can never get to 10 moles of CO2 because at 5 moles, all of the oxygen is gone. So our O2 is our limiting reagent, and the methane is in excess. So how much methane remains? If it's in excess and it all doesn't react, how much remains? So this is a little bit tricky. The way you figure it out is you use your limiting reagent to solve it, because we know that it all gets used up. So we're going to go 10 moles of oxygen, that all gets used up, and we're going to figure out how much methane reacts. So from our balanced equation, 1 methane is reacted for every 2 oxygen. Oxygens cancel out. So this will tell us the amount of CH4 that reacts. So that works out to be 5 moles of methane that reacts. Okay, so we started with 10. So started with 10 moles of methane, 5 moles react. So we subtract that, 5 moles remain. So when this reaction is done, we've used up all of the limiting reagent. So all of the O2 is used up. 5 moles of methane did not get used up. So we say 5 moles remains. See what I mean about these problems taking a while to solve? And this is moles. We still got to do mass, which adds another level to it. Okay, decision time. If you would like, I will do one more of these and then we'll move on to the next step. So we're going to do B. I don't have any space here. 2.2 moles of magnesium and 3.30 moles of hydrochloric acid. What can we do? We'll squeeze some of it in here. Magnesium reacting with hydrochloric acid. Single replacement, MgCl2 and hydrogen gas. Throw a 2 in front of that and it's balanced. Okay, so that was 2.2 moles of magnesium and 3.3 moles of HCl. Okay, so which one is the limiting and which one is in excess? So again, to solve the problem, we're going to solve it twice, once with each amount of reactant. And let's pick, we'll go with hydrogen as our product. So number of moles of hydrogen formed using 2.20 moles of Mg, and then we'll solve it again using 3.30 moles of HCl. Okay, molar ratios. So this one is 1 hydrogen for every 1 Mg. So we get 2.20 moles of hydrogen. Now we'll solve it with HCl. 1 mole of hydrogen for every 2 HCl. So that works out to be 1.15 moles of hydrogen. Okay, so there's the amount of hydrogen using both reactants. The lesser amount is our limiting reagent. So the limiting reagent is HCl, which means magnesium is in excess. So if we wanted to calculate the amount of magnesium that remains, we would start off with our limiting reagent. So number of moles of magnesium. Oh, this is going to get messy. I don't have much room here. So number of moles of magnesium that remain. Start with the limiting reagent. 3.30 moles of HCl times, from our balanced equation, 1 magnesium for every 2 HCl. So that means we will use up 1.15 moles of magnesium, and we started with 2.20. We used up 1.15, so we have 1.05 moles remaining. I apologize for squeezing that in. This is an ugly mess. Okay, that's the pattern. Messy and chaotic, but it is a pattern. So now we're going to do the exact same problems, but this time instead of moles, we're going to use mass. And this is more typical of what the problems look like in Chem 20. So it just adds another step to solving these. And I've left lots of space for this. Okay, so we've got sodium sulfide reacting with dissolved in water and added to a solution of silver nitrate. Sodium sulfide, Na2S aqueous, reacts with silver nitrate, AgNO3 aqueous. This is a double replacement. 2 ionic compounds to make NaNO3 aqueous, and Ag2S. And if you look that up for solubility, sulfide and Ag is not there, it's in the most. So Ag2S is a low solubility solid. So that's what we're talking about with precipitate. So there's our PowerPoint. Precipitate. Okay, we haven't balanced it yet. 2 Na, 2 Na, 1 sulfur, 1 sulfur, 2 silver, 2 silver, 2 nitrate, 2 nitrate. Okay, we're balanced. Whew. Okay, so we have 8.6 grams of this and 10.7 grams of this. By the way, up until this point in Chem 20, you've never been given problems where you've had masses of both reactants. You've always been given only one mass for stoich, and you've been told the other one is in excess, or you just weren't told anything about it. It was just assumed that one of the reactants was in excess. So now when you see a question and you have the masses of both reactants, that's telling you that it's one of these questions where there's a limiting reagent and there's an excess reagent. So you have to go through these steps and figure it out. So the pattern is easy. So let's pick a product. Well, actually it asks for mass of precipitate. So we'll use the precipitate. Let's find out the mass of Ag2S. Mass of Ag2S that's going to form. And we're going to do it twice. Mass of Ag2S. So we're going to start off with one reactant, 8.6 grams of Na2S. And then we're going to solve it for the other reactant, 10.7 grams of AgNO3. And we're going to see which one produces the least amount, and that's our limiting reagent. So this is the only extra step from the previous problem, is we need molar masses. So the molar mass of Na2S is 247.81 grams per mole. So I'll flip it. Okay, 247.81 grams. I think I did that wrong. It's 78.05. Back that up. 78.05 grams per mole. Just verify that. Na2S, yes it is. Okay, so that's going to give me my moles of Na2S, stoichiometry. And I want Ag2S, so here's my molar ratio. 1 Ag2S for every 1 Na2S. Okay, so now I've got my moles of Ag2S and I need my mass. So the molar mass of Ag2S is 247.81 grams per mole. Okay, moles cancel out. It's all about the units, so we will be left with grams of Ag2S, which is what we're looking for. Punch all the numbers in and we get 7.80. All right, so now we just need to find out the mass of Ag2S using our other reactant, AgNO3. So using AgNO3, it is molar mass of AgNO3, 1 mole over 169.88 grams. I got to fix something here. I lied on this mass. I was looking at the wrong one. So when you rub that, some of you, if you're doing on this calculator, you're screaming at me right now, Mr. Johnson, you got it wrong. And it is 27.3. Okay, sorry. So back to this one. Okay, so there's our mass of our reactant, molar mass of that reactant. That gives us the moles of AgNO3, but we want Ag2S. So from our balanced equation, 1 mole of Ag2S for every 2 moles of AgNO3. Okay, AgNO3s cancel out. We now have our moles of Ag2S. Let's get our mass. So this part's easy. It's the same molar mass, same product. Moles cancel out, and here's our 7.80 grams of Ag2S. Okay, so which one will we produce, 7.80 or 27.3? Always the lesser amount. So our limiting reagent is AgNO3. It will be all used up to make 7.80 grams. The reaction will stop. It will never reach 27.3 because we've used up all of our AgNO3 to get 7.80 grams. So you can see why there's a lot of work. You need that balanced equation. You got to solve it twice, once for each reactant. Let's go back and answer these questions. What mass of precipitate is produced? 7.80 grams. What is the limiting and excess reagent? So limiting is AgNO3. Excess is the Na2S. And how much of the excess reagent remains? Whew, last step. I wasn't kidding when I said these take a while. Okay, so we want the mass of the excess. So how much Na2S was used up? Okay, we figure it out using the limiting reagent. So we'll start it again. So what is the mass of Na2S that reacts? Start with the one that we know is all used up, 10.7 grams of AgNO3 times its molar mass. Okay, so now this time we want to find the Na2S from our balanced equation. 1 mole of Na2S for every 2 moles of AgNO3. And the last thing we need is molar mass of Na2S, which is 78.05 grams per mole. So you plug all that in and you get 2.46 grams used up. So how much Na2S remains? Okay, what did we start with? 8.6 grams. And we used up 2.46 or 2.5 if we're going to go with 1 decimal place for our final sig digs, which becomes 6.1 grams remain. There we go. Yowzers. It's a lot of work. It's a full screen to solve that problem. Holy smokes. All right, so here's where we're headed. We're going to do one more of these. If you're feeling really confident, you can go ahead and try this one on your own. The answers are down here at the bottom of the screen. And then you can come back if you didn't get them right and watch the video to see where you made your error. Or you can continue to watch along with me and fill in your notes on this one. And then the assignment will be given on the last page. Okay, so here we go. Last one. In an experiment, we have 26.8 grams of iron 3 chloride FeCl3, iron 3 plus, Cl1 minus, solution, so aqueous, combined with 21.5 grams of sodium hydroxide, aqueous, to produce, so it's a double replacement, Fe3 plus, OH is a 1 minus, so we'll need 3 of those. That's low solubility solid if you look it up. And NaCl, which is high solubility. To balance it, we'll need 3 hydroxides, 3 sodium, 3 sodium, 3 chlorine, 3 chlorine. Okay, there's our balanced equation. Okay, which reactant is in excess? By how much? What mass of each product will be obtained? Okay, so let's go with FeOH3 and solve for that one. We're going to solve it twice. Okay, start off with our first reactant, 26.8 grams of FeCl3, and then we'll solve it again with our second reactant, 21.5 grams of NaOH. Okay, so FeCl3's molar mass, 1 mole for 162.2 grams. Okay, molar ratio to convert that to FeOH3 is 1 FeOH3 for every 1 FeCl3. And molar mass of FeOH3 is 106.88 grams per mole. Moles cancel, and our final mass is 17.659 grams. 17.66 grams. Okay, using our second one, molar mass of NaOH is 40 grams per mole. Molar ratio 1 FeOH3 for every 3 NaOH. And molar mass product is still 106.88 grams per mole. Drum roll, please. We get 19.15 grams if we use up all of the NaOH. Okay, so who's our limiting reagent? The lesser of the two, FeCl3. So what mass of this product will we get? 17.66 grams. Mass of FeOH3 is 17.66 grams. And that means our excess is the NaOH. Which reactant is in excess? NaOH. By how much? Okay, well, how much NaOH reacted? So let's go back and figure it out. The mass of NaOH that reacts, start with the limiting reagent because we know that it's all used up. So 26.8 grams of FeCl3 times its molar mass. Okay, molar ratio, we are looking for NaOH, so 3 NaOH for every, oh dear, this is messy, 3 NaOH for every 1 FeCl3, for every 1 FeCl3. And molar mass of NaOH is 40.00 grams per mole. Okay, so what mass of NaOH reacts? 19.82 grams. And what did we start with? 21.5. So started with 21.5. We used up 19.8. And that means 1.7 grams remains. 1 decimal place. Okay. The question asks for what mass of each product will be obtained. How would you figure out the mass of NaCl. Would you use the limiting reagent or the excess to figure out the mass of NaCl? Correct answer would be, let's start with the limiting reagent again, 20.68 grams of FeCl3. Get its moles, 162.2 grams. We're looking for NaCl, so it's 3 NaCl for every 1 FeCl3, and then we would need the molar mass of NaCl in grams per mole, and that would give you the mass of that product. And I don't actually have it, and that's okay. You could certainly look that up and figure it out. You've got the patterns down. Phew, we're done. Okay, it's a lot of work, those questions. In your study guide, page 240 for Johnson, 244 for Kelly. There are 2 limiting excess reagent questions to do. And IONS, I will post the answers to those. If you would like additional practice in your textbook, there's a question as well, and the answers are in the back to self-check on that one. So that's 3 of these questions in total. They take 5 to 10 minutes each, so that's lots. You'll get the patterns down. Again, this is a tough one. It's just, there's a lot of steps. It takes a lot of time. You got to get the molar masses. There's no shortcuts to these problems, so you got to be careful and work your way through them, but you can do it. Yes, you can. Okay, so work on those, please. And remember, we're just a few days away from wrapping things up. This is one of our last topics, so that's kind of exciting. Okay, good luck on those, and I'll see you soon.